First of all, on behalf of ISSMG, I would like to thank the organizers of the third ISFOC symposium for hosting the third Mcclelland-lecture in such a prestigious venue. It was the best of times. It was the worst of times. It was the age of wisdom, the age of foolishness. It was the season of light. It was the season of darkness. It was the spring of hope. It was the winter of despair. I feel that those words by Charles Dickens are very fitting to what we are experiencing tonight. It is the worst time of foolishness, darkness, and sometimes despair, because the oil and gas industry has been undergoing a significant cost-cutting due to falling oil prices, and too many companies are laying off too many of our colleagues. The industry is going through yet again a bust cycle. And despite the great attendance tonight, a lot of our colleagues that wanted to be here were not allowed to travel because of budget constraints. But tonight is the best of times. It's a moment of wisdom and light when we stop, we reflect, and we take the time to recognize a giant in our discipline. So the Mcclelland-lecture was officially established in 2010. It's the only global recognition that is dedicated to offshore geotechniques, and it honors the legacy of Mr. Bram McClelland, offshore pioneer and visionary. The third Mcclelland-lecturer is Knut Andersen. Knut was born and raised in Oslo. He first went to work for NGI for his master's thesis in 1968. Dr. Laurits Bjørn, the NGI first director, followed the work very closely, gave him encouraging comments and input, and offered him a job after his thesis. And so Knut started working for NGI in 1970, and the continued cooperation with Dr. Bjørn until his premature death in 1973 really shaped Knut as an engineer and was decisive for his professional career. In line with NGI's philosophy, Knut has worked on both consulting and research projects, taking advantage of the beneficial interaction between consulting and research. Knut possesses a quiet but resolute leadership, an unblemished intellectual honesty, and ethics of the highest standards. One of his highest achievements by far is that he's been the best mentor at NGI, having nurtured hundreds of NGI engineers in the art of science and geotechnical engineering. But don't let that quiet demeanor fool you. He's ferociously determined and actually a very fierce sport competitor. I'm told he once led an NGI basketball team called the Killer Club. And he managed to send a fair number of his colleagues to the infirmary until the NGI managing director had to put a stop to it. And I'm told he even made a job offer contingent upon joining his basketball team. So don't challenge Knut to a game of basketball would be my advice. Knut Technical's achievements are numerous, and they are detailed in the proceedings of this symposium. Offshore foundation engineering has been the focus of his work and his career since 1972, and his work with Dr. Bjørn on the Ekofisk field. Knut's name is forever linked to most of the gravity platforms installed in the North Sea, for which he developed foundation design parameters, practical design methods, interpreted model test, and prototype monitoring. Knut's name is also closely associated with the design of suction anchors, for which he led the development of design methods in the 1990s. Most suction anchors around the world have been designed or somehow verified by Knut. And along with colleagues from Statoil, NGI, and Shell, Knut was inducted into the Offshore Energy Hall of Fame for his contribution to suction pile technology. Knut has led 12 JIPs over the years. The first one was in 1974. And the subject, you might have guessed it, was the cyclic behavior of clays. So what we will hear tonight is really crystallizing 40 years of experience and industry leadership. Knut has been keynote lecturer and chairman at numerous international conferences. He was the 21st Mcclelland-lecture in 2007, and he delivered the distinguished lecture at the Memorial University in Newfoundland in 1997. He is author and co-author of more than 100 contributions to professional journal, books, and conferences. He was the technical director at NGI from 1996 to 2012. He reached retirement age in 2012 and now serves as technical director. This is only a partial list of Knut's accomplishments, but listing them all would only delay the wonderful moment when I'm privileged to say ISSMG is proud to welcome Knut Andersen to deliver the third Mcclelland-lecture.
Thank you, Philip. I understand that you have done some research into my background and got some inside information. But I feel honored to have been asked to give this third Mcclelland-lecture, and I would like to thank the TC209 committee for appointing me. The main goals of my presentation is to present the Cyclic contour diagram framework and a database with contour diagrams and correlations of required parameters. Contour diagrams and the construction of such diagrams are known to some of you, but then in addition to explaining the concept, I will also point out some aspects that are less known, and also I will tell how they can be applied in design. The database contains contour diagrams for different soils, sand, silt, and clay. And it also contains correlations of static and cyclic shear strengths and shear strengths with index parameters. The paper also contains correlations of non-cyclic parameters like static strength, initial shear modulus, friction angles, and consolidation characteristics. This is the presentation or the content of my presentation. I will start talking about when do we need cyclic soil parameters, what parameters do we need, how does soil behave under cyclic loading. Then I will explain the cyclic contour diagram framework, how the contours are constructed, what the important parameters are, and also a database with the diagrams and correlations. I will then talk about or tell about how the contour diagrams can be applied in design, calculation procedures, slope stability or slope instability due to cyclic loading like earthquakes, and finally verification of the use of contour diagrams by comparing calculations with measured prototype and model test observations. The presentation that I will make today will be a light version of the paper, and you will find much more details in the paper. In particular, calculation procedures and slope instability due to cyclic loading will not be covered in the presentation that I will make today. And also some of the correlations can only be found in the paper. So, when do we need cyclic soil parameters? My first involvement with offshore foundation design was in connection with the Ekofisk tank, which was installed in 1973. Mcclelland engineers were responsible for the site investigations, and they had significant experience from the Gulf of Mexico, and we benefited greatly from their experience at that time. I did not have the privilege to meet Mcclelland himself, but I met many of the Mcclelland engineers, and that gave me a very good start in my career for the offshore work. After the Ekofisk tank was installed, things happened very quickly, and we got into a very steep learning curve. Already 2 years after the Ekofisk tank was installed, 2 of the large condip platforms were designed and installed. And also in that period, the industry saw the need to know more about cyclic soil behavior, and 12 industry sponsors initiated a joint industry project on cyclic loading on clay. And that was the first joint industry project offshore at NGI, and we have then had many more after that. But we need to know cyclic soil behavior not only to design the large gravity platforms, it's also important to know cyclic soil behavior in connection with other foundations, like foundations for TLPs, anchoring, suction anchors for other type of floaters. More recently, it's also required in connection with the foundation design of wind power structures. And they pose additional challenges, both because of the new, or at least partly new, type of foundations, but also because they are placed closer to shore. It means that we get into more complex soil foundations with more layering and varied soil, sand, silt, and clay of different densities. It's not only offshore that we need soil parameters for cyclic loading. It's also in connection with sea protection barriers, coastal structures, ice loading from drifting ice, and this will also be very important, of course, if the industry goes into the Arctic. Also in connection with earthquake, cyclic soil behavior is important, both in connection with the bearing capacity of structures during earthquake and also for instability that can be induced by earthquakes. In order to make sound foundation design for cases with cyclic loading, we need to address the topics that I've listed here. We need to determine bearing capacity under cyclic loading. We need to calculate cyclic displacements. We need to determine soil stiffness for use in global dynamic analysis. We need to calculate permanent displacements due to cyclic loading, both due to dissipation of excess pore pressure that is generated, and also due to the increased average shear strains during cyclic loading. Soil reactions will also be influenced by the cyclic loads, which may cause redistribution of reactions. And finally, we need to determine how the static capacity is reduced by cyclic loading. So what parameters do we need in order to address these topics and to make design for this? We need cyclic shear strength, cyclic shear modulus, permanent shear strain due to cyclic loading, pore pressure generation, recompression modulus to calculate the volumetric strain when the pore pressure dissipates, damping, and static strength due to cyclic loading. All these topics are covered in the written version of the paper, but today I will concentrate on the 4 first ones. Before we determine the soil parameters, it's important that we understand what is happening to the soil when it is subjected to cyclic loading. I've illustrated that here by an effective stress path, which shows the behavior for a test with monotonic loading on a contractive soil. This is undrained behavior. And you see that the stress path will go like this. It will reach a peak, and then it will reach the failure envelope, and it will then experience strain softening as it's going down along that failure envelope. For cyclic loading, where we cycle with the cyclic amplitude around an average shear stress, we also start here, and during the first quarter cycle we go up here. But when we then reverse, we get an effective stress path that forms a loop. And this loop does not close. So it means that after one cycle, we have generated a permanent pore pressure. And this pore pressure will accumulate with or increase with number of cycles. And we move to the left in this diagram. And the effective stress path will finally reach the failure envelope, and large shear strains will then develop. This is illustrated in another way in this diagram. It shows how the pore pressure develops with time. And as I said earlier, that pore pressure will increase with number of cycles, and therefore also with time, both the cyclic amplitude and the permanent pore pressure. This means that the effective stresses goes down, and therefore the shear strains will also increase with time. Both the cyclic amplitude and the average shear strain and the permanent shear strain. I explained these components more clearly in this picture. This is a stress-strain behavior after the first cycle and after a cycle N. And the cyclic shear strain is then defined as half the difference in peak-to-peak shear strain. And the average shear strain is half the sum of the peak-to-peak shear strains. The gamma p is the shear strain that will be there when we have completed the loop, so that after we have completed the cyclic event, we will sit with a permanent shear strain, gamma p. We need these shear strain components in order to calculate cyclic displacements and the soil stiffness for dynamic analysis. We need gamma cyclic for that. We need the sum of gamma A and gamma cyclic in order to calculate the total or maximum displacements. And we need the gamma P to calculate what the shear-induced displacements will be when the cyclic event is over. These do not describe what is happening within the loop, the details of the loop, but we have developed a model where this also can be described, and that's described in a paper to this conference by Amir Kenya and myself. So, in order to determine these components, we need to perform laboratory tests. And this shows the results of 3 such laboratory tests that we run in order to determine these components. The first one is a cyclic simple shear test with symmetrical cyclic loading. And you can see here the response. It's a reasonably symmetrical cyclic shear strain development. If you perform a triaxial test, also with symmetrical cyclic loading, you will see that the behavior is different. We get relatively large cyclic displacements, but in addition, we get a permanent or an average shear strain, which is of the same order of magnitude. And it's also going to the extension side. And the reason why it's going to the extension side and that it's not symmetrical is that the soil behavior is anisotropic. The extension strength is lower than the compression strength. So with a symmetrical cyclic loading, we mobilize a larger part of the strength on the extension side than on the compression side. And therefore we get this non-symmetrical behavior. The third example is a triaxial test with one-way cyclic loading. And there you will see another behavior which is also different from the two first ones. In this case, we get relatively small cyclic displacements, and it does not increase very much with number of cycles. But the average shear strain develops, and that will be the failure mode in that situation. This shows another aspect. It compares triaxial tests which have been performed with the same maximum shear stress, but with different amplitudes. And if creep should be the explanation for the development of shear strains during cyclic loading, the amplitude shouldn't mean very much. But these examples show that creep is not the only explanation, at least, for what is happening during cyclic loading. The first example is a two-way cyclic loading, and that test failed in 10 cycles with large cyclic shear strains. Test number B was a one-way cyclic test with the same maximum shear stress, but with a lower, of course, lower minimum stress. That test survived 2,500 cycles. And at the end of 2,500 cycles, it had a permanent shear strain of 0.8% and a cyclic shear strain of 0.3%. The last test had a smaller amplitude, and it also survived 2,500 cycles, but the shear strains were then only 1/10 of test number B. So this means that the cyclic behavior depends both on the test type and also on the combination of average and cyclic shear stresses. In a foundation design, or in most foundation design, we have a lot of different stress paths. And this is one example where you can see that we have both symmetrical and non-symmetrical DSS tests, and we have triaxial compression tests that will be both on the compression and the extension side and with different average shear stresses. So we need to kind of organize the results that we see in these different tests so that we are able to apply them in design and determine the parameters that we need in design. And one way to do this is the cyclic contour diagram framework. And the construction of these diagrams we use the philosophy that since the behavior depends on both test type and average and cyclic shear stresses, we develop separate diagrams for DSS and triaxial tests. And we plot the results as functions of the average and the cyclic shear stresses. This shows the results of tests with different combinations of average and cyclic shear stresses. And the numbers that are written along the various data points is the number of cycles to failure and the average and the cyclic shear strains at failure. And when we have these results, we can draw contours through the data points. And if it's a homogeneous clay with little scatter, you will see that you are able to establish contour diagrams like this. The curves show the number of cycles to failure as a function of the various combinations of average and cyclic shear stresses. The intersection point with the horizontal axis is the static strength. If you have no cyclic shear stress, then the soil can carry the static loading, or it can go up to the static shear strength. Along this axis, cyclic failure mode is large cyclic shear strains, and that's the predominant failure mode in the part of the curves that are drawn with red color. The blue curves in that region, the failure mode is large average shear strains. This shows an additional diagram. It shows the number of cycles to failure as a function of the cyclic shear stress. And this is the failure line that can, and this is established for the condition of average shear stress equal to 0, meaning two-way cyclic tests. And this curve is actually a section to this diagram for tau A equal to 0. We can do exactly the same for triaxial tests, run tests at different combinations and draw contours. The contours are not symmetrical for the reason that at least this soil, which is Drummond clay, is anisotropic. So you have the compression strength here and the extension strength here. In this diagram, the failure mode will be large cyclic shear strains in this part, large average compression strains in this part, and large average extension strains in that part. When we perform a stability analysis, we need the cyclic shear strength. And the maximum shear stress that we can mobilize is the sum of the average and the cyclic shear stress components. So what we need is the sum of these, and when we have this diagram, we can easily convert this diagram into this diagram, which has the same horizontal axis, but on the vertical axis we have the cyclic shear strength defined like this, which is established by just going in for various tau A values, reading out tau cyclic, adding them and plotting them here. The diagrams may or has a shape that may be a little surprising, since we have the static strength here, and you can see that we for one cycle we can actually apply a cyclic load, or the strength is actually higher than the static strength. And the reason for this is that we perform the cyclic tests with a load period of 10 seconds. And the reference static strength is from a test that is brought to failure in approximately 2 hours. So that's why we have this shape of the diagram that we can apply higher shear stresses under cyclic loading than under static. But of course this is related to the load period, which is 10 seconds in this case, and the rate of the static test. So we need to keep that in mind. So if we have conditions that are different, with for instance a different duration of the average load, or with a different load period for the cyclic loading, we need to make some adjustments. I'll come back to the effect of load period later. We do the same for triaxial. It's one step more complicated because we have a compression strength here. Then we add tau A and tau cyclic, and we get this diagram. But we also need to consider what is the extension strength, and then we are on the opposite side. So then the strength will be the difference between tau cyclic and tau A. And therefore we get this discontinuity for the triaxial strength. And we have defined compression strength when you have an average shear strain, which is 0. Then that's the difference between compression and extension. So when we have a positive average shear strain, we define this as compression. When it's negative, we say that it will fail in extension. So that's the reason for this discontinuity. But we need also information about the strains, not only the strength. And we follow the same philosophy and plot the data from the tests. This is the strains, average and cyclic, after 10 cycles. And it's plotted in the diagram just as we did for number of cycles to failure. And we can draw contours just like we did for the strength. We have the red curves indicate the cyclic shear strain. The blue are the average shear strains. We need to do this for different number of cycles, and this shows for 10 cycles, this shows for 100 cycles. Again, the diagram that perhaps many of you are familiar with and which has been used for many years. This is valid for an average shear stress of 0, so it's a two-way cyclic loading. This diagram is connected to these contours. As tau A is equal to 0, the n equal to 100 will be data points along the vertical axis here, and it's also data points along this section for n equal to 100. And the same for n equal to 10, data points here and here. And we can actually combine these different contours, both with the number of cycles to failure, shear strains, and log n diagrams into a three-dimensional plot like this. It's illustrating the behavior, but it's more difficult to apply in design, but this is the connection between these different contour diagrams. We have the same for triaxial, established just like simple shear. We established them for different number of cycles, and this defines the red cyclic shear strains and the blue the average shear strains. Pore pressure, exactly the same. DSS tests for n equal to 10, triaxial, and also pore pressure as a function of number of cycles for a given tau A. So when we know the shear stresses in the soil, we can go into these diagrams and determine what is the pore pressure. These contour diagrams can be used for several purposes. One is to use them directly in design, which we often do, and I'll come back to that. They also provide a good basis for developing more sophisticated constitutive models. And also, I think when you have a constitutive model, I think to reproduce these diagrams with your constitutive models would be a very good check of the quality of your constitutive model. They also provide a good framework for planning and interpretation of site-specific cyclic laboratory tests when you come to a new site. And I'll also come back to that. So as you understand, at NGI we use these contour diagrams for many purposes. And it also includes cake decorations. And we also, as I guess Philip was not aware, but we also used them to put some science into sports. And this is our basketball version. When we construct these diagrams, there are some parameters that we need to keep in mind. And there are 4 of them that I would mention today. And one is the difference between stress and strain controlled cyclic loading. The other is effective load period, and then preshearing, and the difference between, or the effect of applying to a drained or undrained. The contour diagrams that we normally establish or construct is based on stress control tests, meaning that we perform tests at a constant cyclic shear stress amplitude and determine the strain contours based on that. In earthquake, and one reason for doing that is that normally we work with designs where the loading is in terms of specified forces and a load composition where we know the forces. And it's much more easy to relate that to shear stresses than to shear strains. So I think that's one good reason to work with stress-controlled cyclic loading. For earthquake engineering, it may be a different story because the loading is defined in different ways. And earthquake engineering, they very often use strain control tests. But it's important that we are aware of the difference between these. I have one example here where I have the result of a strain-controlled test with a strain amplitude of 1.5%. And you can see that plots very different from the strain contour for 1.5% from the stress control tests. And there is a simple reason for that, and that's that after 100 cycles, for instance, the strain control test has been subjected to 100 cycles at 1.5% shear strain, whereas the stress control test has 1.5% shear strain only in the last cycle. And it's starting with 0.5% and is building up. So it's a much more severe cyclic loading if you perform strain control tests than if you perform stress controlled. So that's important to keep in mind. We are able to determine the behavior of a strain control test based on the strain contours from stress control test, as you can see with the red curve here. That has been constructed by the strain accumulation procedure, which is described in the paper, and that I will also come back to. This shows the effect of load period. It's the load period on the horizontal axis, and it's the number of cycles to failure divided by the number of cycles to failure for a 10-second load period. And this diagram shows that with 10 seconds, that's set equal to 1. If we have a 1-second load period, we can actually apply something like 5 times as many cycles before it's failing. If we have a 100-second load period, there is significant scatter, but typically we could apply only 1/5 of the number of cycles compared to 10 seconds. A sand deposit where we place a platform will often have some cyclic loading accompanied with drainage before we get the main cyclic event. Or there may be some drainage during the build-up of the design event. This will influence the behavior during the subsequent undrained loading event. And I've tried to illustrate the effect here. With preshearing, we mean a number of cycles at a given cyclic shear stress and accompanied by drainage. Typically, we apply 400 cycles, and that's at least most of the data in this diagram. On the vertical axis, you have the undrained shear strength, cyclic shear strength of a sand or a silt after 10 cycles. And the curves down here, they give a low cyclic shear strength, and meaning that it's a loose sand or silt. Up here, you have a high cyclic shear strength, meaning that we work with, or that it represents a very dense sand. And you can then see here the effect of applying preshearing. You have zero preshearing along this axis, and you can see the effect that it will have. Depending on the level of preshearing, the undrained strength during the main cyclic loading will increase by typically something like 20 to 50%, depending on the amount of preshearing. What is surprising is that if you look at the very dense sand, you see that the effect is equally strong. You would perhaps expect that the loose sand has most to gain by preshearing, but that is not the case. So it has to do with the structure. And also the volumetric strains that you see during this preshearing is very small, at least for the very dense sand. So it has to do with the structure that is building up. If we apply preshearing that is giving large shear strains, we may get the opposite effect. We may get a latency and the drainage, and that may reduce our density, and we may get a negative effect if the preshearing is too strong. This shows the effect of preshearing for clays. The left diagram is for normally consolidated clay, and the test is run by applying 400 cycles of an undrained or of a cyclic shear stress that is of the order of half the undrained shear strength. And you can see that the pore pressure builds up, and then we let it drain. We repeat the undrained cyclic loading, and you can see that the build-up for each repetition becomes smaller with increasing number of series that we apply. The effect on the strains is not so significant, but it's a positive effect, a clear positive effect on the pore pressure. If you do the same with an over-consolidated clay, you will see the opposite effect. During the first 100 cycles, we build up some pore pressure. It dilates to begin with, but then it builds up a positive pore pressure. When we drain it out, the pore pressure, and repeat the undrained cyclic loading, you can see that for each series, we build up more and more pore pressure. And if you look at the cyclic shear strains, they will become larger and larger for each repetition that we make. So there is clearly some degradation of over-consolidated material that we should be aware of. For gravity platforms, this may not be so important, because the gravity platforms are normally designed by assuming that the design event comes just after installation. And when we then have cyclic loading or dissipation of the pore pressure, it means that at the same time we will get an increased effective stress due to the consolidation under the weight of the platform, which will compensate for some of the pore pressure buildup, or the increased pore pressure buildup. If we have a monopile, for instance, we may need to be more careful, because there we do not, on the sides, we do not have the beneficial effect of increased effective stresses due to the weight with time. The last of the parameters that I wanted to comment on is the importance of whether the average shear stress is applied drained or undrained, or it's actually the change in average shear stress. I've illustrated that by two load histories. One where the average shear stress increases quite rapidly, and one where the average shear stress increases more gradually. For clay, TOA the soil will be undrained during application of TOA. But for sand and silt, the soil may be undrained or drained depending on whether TOA is increased rapidly or slowly. Most likely it will be undrained during this type of loading, but drained under this type of loading. Whether it's drained or undrained will depend on also on the drainage path, the dimension of the structure, and the consolidation characteristics, of course. But the implication for the shear strength, cyclic shear strength, is quite significant. This shows the diagram if we apply the average shear stress undrained, and this if we apply it drained. And as you can see, the strength is much higher for the undrained application than for the drained when we come to this part of the diagram. Along the vertical axis, they are the same, because if you have no TOA, then they are identical. We have the same for triaxial. And for the triaxial, the intersection points with the horizontal axis, that's the static strength. And that will depend on whether we apply the average shear stress by changing the vertical stresses or the horizontal stresses. They will follow different drained effective stress paths, and that's so therefore they also you get different drained shear strengths for these cases. And as you can see, the diagrams are very different. I have tried to put some numbers on what the effect can be by an example where I assume that we have a ratio between toe cyclic and the change in average shear stress of 1.5. And then I read out the shear strength for extension and compression and DSS, that's not shown here, but it's done in the same way, both for undrained and the drained case. And then I calculate the ratio between drained and undrained cyclic strengths. And it depends on the type of test, but the average ratio is that the drained strength is 65% of the strength under drained toe A application is 65% of the case where we apply toe A undrained. The strength is undrained because the cyclic loading occurs under undrained conditions in both cases. If we just look at some example, what could this mean? If you look at a pod that is in tension and one that is in compression, and we assume that the strength along a potential failure surface is the average of the three, you will see that the ratio between the strengths for drained toe A and undrained toe A is as low as 0.3 for the tension case and 0.83 for the compression case. And this is for a very dense sand, and it's for 10 cycles to failure, and it is for a ratio of toe cyclic over delta toe A of 1.5. If the density goes down, the effect will go down. But if we reduce this ratio, then the effect will be even larger. So when we do a design, it's very important for us to get good information about the cyclic load history, because that can have very big consequences for the foundation design. I will now show you some examples of the database that we have in the paper. This database can be used for directly in feasibility studies, and it can also be used to establish site-specific contours. Our strategy to construct site-specific contours or to apply the database would then be that we first try to find contour diagrams in our database from soils that are similar to the ones that we have in the case that we want to investigate. Then we could run some monotonic tests, DSS, triaxial compression and extension, and a few, for instance, 3 cyclic tests with different combinations of average and cyclic shear stresses, and compare to the diagrams that we have in the database. And if we get a good match, then we can be happy and use that. If we do not get a good match, we may need to supplement with more tests in order to determine the full contour diagrams. But it's not in all cases that we would need the full diagrams. For instance, if we have a gravity platforms where horizontal sliding is the critical failure mode, and we know that or have a suspicion about that in advance, we only need to perform tests along this axis, and we can reduce the number of tests considerably. So that's a consideration that one need to make. This is an example of the type of contour diagrams that you will find in the paper. This shows cyclic shear strain and pore pressure as a function of cyclic shear stress and the number of cycles. This is for a DSS test with symmetrical cyclic loading. And in the paper you will find similar diagrams, both for DSS and triaxial test with different relative densities. If you are able to see it, you will see that the cyclic shear stresses are normalized not directly by the consolidation, the effective consolidation stress, but to a stress that I called sigma-ref. And this sigma-ref is defined as the effective consolidation stress to a power of n. And I'll come back to the reason for that later. The paper also contains diagrams with this type of plot, which shows number of cycles to failure as a function of both tau A and tau cyclic, both for triaxial and DSS, and also for both drained and undrained application of delta tau A. This is number of cycles to failure. And this is showing the same type of diagrams with shear strains, cyclic and average. And we also have that in the paper for various densities and also for different number of cycles. The paper also gives various correlations that can help to construct the diagrams, both for clay, silt, and sand. And at least for clays, or also for, well, in general, we need the static strength, since that defines the intersection at the horizontal axis. And also for diagrams for clay, they are normally normalized with respect to the undrained static shear strength. So we need it in order to denormalize our diagrams. This plot shows the undrained static shear strength normalized with respect to the vertical effective consolidation stress. And it shows data for different plasticities. I have just indicated above and below plasticity index of 25%. And if you inspect this closely, you will see that the static strength normalized with respect to the vertical effective consolidation stress is not a constant. It increases with decreasing vertical consolidation stress. And therefore, we have introduced this sigma ref. And in order to determine what this exponent should be, we have done that by curve fitting, and have found that for clay, an exponent of 0.9 would be a reasonable fit. And if we use that, we get the curve that you see here when we plot it as a function with normalization to the vertical effective stress. So that's one reason for using that. When we come to static strength of sand and silt, the exponent varies between 0.9 and 0.1, and I'll come back to that later. For cyclic strength, the exponent is also of 0.9 is also giving a good fit based on the data that we have. When we plot this shear strength normalized with to the reference stress, we get data point like this when we plot it as a function of plasticity index. And you will see that the strength is not a strong function of plasticity when we have a plasticity above something like 20% or 22%. But when we come to a lower plasticity, there is more scatter, and it seems like the normalized strength increases. So when we come into this region, we should also consider the correlations that you will see later, which are valid for sand and silt. This shows a correlation of cyclic strength. It's for DSS tests on clay with symmetrical cyclic loading. And it shows the ratio between cyclic and static shear strengths for 10 cycles of loading. And you can see that in this case, the effect of cyclic loading depends strongly on the plasticity index. So for high plasticity clays, with n equal to 10, you have a cyclic strength which is close to the static strength. But when you come to lower plasticity clays, you have a much more significant effect of the cyclic loading. And this curve is actually giving us the intersection point up here in this diagram. For sand and silt, we have these correlations. This is the static strength for symmetrically loaded DSS tests, normally consolidated material. We have water content on the horizontal axis in this plot and relative density on the left side. The static strength is normalized to this reference stress, and we have 3 curves, and the difference between them is that this curve, the fully drawn curve, is for sand or silt, or it's for sand with fines that has it's less than 5% 5 content. So it's a clean sand. If we look at tests on sand which has some silt in it, this is with 20% fines, and then we get this curve. If we have 35% fines, we get the curve here. And the corresponding curves here if we define it in terms of relative density. If we increase the fines content to a greater percentage than 35%, the strengths will start to go up again. And we will end up something in this region, which would be what we have for clays. So 35% fines content is some sort of a worst case with respect to grain size. The numbers along the data points, by the way, that is the silt content. So that's the basis for distinguishing the data and to draw the different curves. You also may notice here that in this table I give the exponent that we use to determine this reference stress that we use for normalization. And it's a bit more complicated than it was for clay. We find that it's the exponent, the best fit we get if we have a low exponent up here when we have a normalized strength greater than 5. And it's becoming higher when we come down to this region. Then we can use 0.9. And the reason why there is a difference here is that when we have a very dense sand, which is what we have up here, the strength is mainly governed by the latency. So the effective stress is not important. And therefore, we use a small exponent, which is reducing the effect of the consolidation stress. You may also notice that the strengths are extremely high. So if you have a situation where you have a clean sand or a clay with relatively little fines content, the strength is in practice almost infinite. And in agreement with what Tor Inge said in his keynote earlier today, it's almost impossible to get a failure. But if you have but of course it's governed by cavitation, so it then depends on the water depth, how high you can go here. But one should be a bit careful, because if you have a lower density, or if you have a high fines content, it may fail by large shear strains before you reach the cavitation pressure. So it is necessary to do this evaluation. The diagram that I showed you was for DSS tests. This includes the data from triaxial compression tests with the red triangles. If you are able to see the numbers, you will see that the numbers for these are relatively low, of the order of 2% fines or lower. And that means that the triaxial compression strength is significantly higher than the DSS tests with the same fines content. We also have data here for triaxial compression strengths with a higher fines content, and you can see that these are also significantly higher than the corresponding curve for DSS tests. The blue triangles are triaxial extension tests, and if you inspect this closely, you will see that they are much more closer to the DSS strengths. We have a few cases where we have sets of compression, extension, and DSS tests, and I plotted that here. We have it for different relative densities. And the plot shows ratio between compression and DSS strengths and extension and DSS strengths. So you have the compression over DSS here, extension over DSS here, the average of compression and extension divided by DSS here, and 1.0, that's the DSS. So you can see that for low relative density, the DSS strength is close to the average, which is in line with what we often see for clays. But when we come to high densities for sand and silt, you will see that there is a significant anisotropy where the average of compression and extension is significantly higher than the DSS. This shows the cyclic shear strength, DSS test, normally consolidated, 10 cycles. and it's not showing the same high strengths as the static, but you can see that for high densities we also get relatively high cyclic shear strengths. And also for the cyclic strength there is a clear effect of fines content. We need these data to determine the intersection point here, and I didn't mention it, but for the static strength, of course, gives us this intersection point on the horizontal axis. The exponent for this sigma ref that I use for normalization is 0.9, which seems to give a reasonable fit with our data. The cyclic data or the cyclic strengths I've shown you are for 10 cycles. And of course that's not the magic number, but it's convenient to use for these diagrams. And you can then use this plot if you want to find out what is your cyclic strength for other number of cycles. This shows the cyclic strength as a function of number of cycles, and the soils where you have a low cyclic strength, here is of course a sand with a low density, and the ones that are on the top here, they are soils that are very dense. The same data is normalized here normalized with respect to the strength for 10 cycles, so that you get some impression. But it's the same data in these two plots. All the plots are for normally consolidated soils. And this shows what is the effect of our consolidation ratio. And this is actually a plot that I have become quite happy with. I struggled a bit with it to start with, but it is showing the ratio between strength for over-consolidated material normalized with the strength for normally consolidated material as a function of the over-consolidation ratio. And as you can see, there is a significant range in this plot. It includes both static tests and cyclic tests, and both compression, extension, and DSS. The upper part of this scatter is what you will get if you have a soft clay, which contracts when it's sheared undrained in the normally consolidated state. And if you use the Schanzepp equation with an exponent of the order of 0.8, you will get this curve. But then we have data for very dense sand, which actually plots down there. And if you should fit it with the Schanzepp equation, you would need to use a very low exponent. Meaning that the effect of our consolidation is very small for dense sand. And the reason for it is that this very dense sand, it dilates already in its normally consolidated state. So the strength is mainly governed by dilatancy. And it doesn't really matter very much what effective stress you start with, because that will become small compared to the effective stress that you develop due to dilatancy when you shear it. So I think that's a reasonable explanation. And we have data in between for clayey silt and clay tilt. And these soils, they can't really decide whether they should contract or dilate. but they contract to start with, and then they decide that they want to dilate. So they are somewhere in between, and they also, the effect of our consolidation ratio is actually also in between the soft clay and the very dense sand. The next topic is how do we apply these contours in design? And in a real design situation, we normally have a storm where the average and cyclic shear stresses will vary from one cycle to the next, whereas our contours are based on tests where we have a constant average and cyclic shear stress for each test. So we need then to transform the storm into an equivalent number of cycles of the maximum wave that gives the same effect as the irregular cyclic history. And we have procedures to do that. We have the pore pressure accumulation procedure and the strain accumulation procedure. And I think they are both applicable and can be used. There is no time for me to go into details on these procedures, and I will have to refer you to the written paper, but you will find them there. They are also to some extent published earlier, but there are some additions and refinements in the paper compared to previous publications. But when we have determined the equivalent number of cycles, we can determine strengths and deformation properties. One information that we need in order to do that is where are we in these diagrams? And we need to determine what is the combination of cyclic and average shear stresses, because that will determine where we are in these diagrams. One simple assumption is to say that the ratio between cyclic and average shear stresses is the same as the ratio between cyclic and average loads. And I've shown that an example with that here, where this is where we would then be along a 45-degree line in the DSS plot, and we would be along the dotted line on the compression side in Triaxial, and here on the extension side. But if you inspect this diagram more closely, you will see that they don't really keep together. Here you will have a combination of average and cyclic shear strength and failure, which is 15% average and 0.5% cyclic. If you go to this diagram, you will see that in compression you have a cyclic shear strain that is 1/10 of what you have in the DSS. And on the extension side, you actually have failure with large cyclic shear strains and small average shear strains. So this doesn't really keep together. They are not compatible. And we have developed a procedure where we can take this strain compatibility into account. It's a limiting equilibrium approach where we have, in addition to the diagrams, we have used the assumption that we should have strain compatibility along the potential failure surface and the condition that there should be equilibrium between the average shear stresses and the average force. And with these assumptions, we can determine by means of some iteration what is the critical shear strain combination and also what is the strength and the capacity. If we do not go that far, we can do a somewhat simpler approach and say that, okay, we think one of these, DSS, compression or extension, is the dominating type of element. And if we do that, for instance, say that we think DSS is the most important stress path in a given situation. We say that, okay, then we think that this is also the critical failure mode. The other elements have to follow. And then we know that we would be here with on the extension side and up here on the compression side. So we know where we should end up, and then by some engineering judgment we can draw how these stress paths would deviate from the dotted lines. Of course, this is an assumption, and it will be an approximation. If we do that, we know where we are in these diagrams, and we can establish, in addition to the strength, we can establish stress-strain curves that we can use as input to relatively simple finite element programs. We can determine the stress-strain curves relating cyclic components, stress and strain, by reading out corresponding values of the cyclic strain contours and the cyclic shear stress. And this shows you an example of that. We can do the same for the average component of shear stress and shear strain by, on the same line, reading out corresponding values of average shear strain and average shear stress. And we will then end up with these curves: compression, DSS, and extension, and model that in our finite element analysis. A more sophisticated and accurate procedure is to implement the contour diagrams into the finite element programs and let the program find out how it is, what path it wants to follow by having strain compatibility and equilibrium between stresses and forces. And there are two finite element codes that have been developed by Hans-Petter Jostad at NGI. One is based on undrained conditions during the whole storm, and one takes the effect of drainage that may occur during the storm into account. And Hans-Petter will present the result of, or present one of these programs in a keynote lecture tomorrow. The last item on my agenda today is to show you some examples where we compare calculations that we have done with this framework with prototype observations and the results from model tests. I will present 3 cases, one for of a consolidated clay, one for a very dense sand, and one for a very soft clay. There are also other examples in the paper that you can study if you want to. The first example is the Condip Brent B platform, which was heavily instrumented and where there was a quite significant storm the second winter after installation, where the significant wave height was 10.3 meters. And the accelerometers gave us information. By double integration of these, we got the displacements during the storm. The cyclic horizontal displacement is plotted here, and the horizontal load on the vertical axis. And the red curve and points are the rotations, and the blue curve and the blue points are the horizontal displacements. The rotations are given here, by the way. The moment and the cyclic rotations are given on the other axis. And as you can see, the ratio between calculated and measured values are in reasonable agreement. It's not a perfect match, but the calculated rotations were 6% greater than measured, and the calculated horizontal displacement was 70% of the measured. The second example is a centrifuge test on a very dense sand, and it's a platform which actually is very close to the Ekofisk tank. The dimensions are the same, the water depth is the same. It's also very dense sand, but it's not Ekofisk sand, it's another sand. The tests was performed by applying a storm which is similar to the design storm for the Ekofisk tank, where we have included load and material coefficients. The characteristic horizontal load is 786 meganewton. So this is where we would be at the predicted failure for the Ekofisk tank. This plot shows the horizontal displacements on this axis and the horizontal load on the vertical axis. Yeah, and yes, I should also say that since we did not get failure, we had planned to just increase the storm by 50% and apply that storm again after the first storm, and also to increase the storms if we did not get a failure, because we were aware that we probably would not get failure. So we had prepared for that. And you can see that the agreement between calculated and measured displacements are very good when we are down here at this level. When we come to the larger storms, you can see that we are a bit more optimistic than what we measure. And the reason for that is that when we came up to this level, we actually got cavitation underneath the heel of the platform. So we got cavitation during storm 3 locally here. And therefore, when we went to storm 4, reduced the loads a little, we still got more displacement because cavitation had already started and done some damage to the foundation. So I think from this we can see that the sand is able to carry very large negative pore pressures, and they can be as large as you reach cavitation, even locally underneath the platform. But that cavitation is important to take into account. We can also see from these results that when we come to dense sand, it may not be the capacity that we should be worried about, but displacements. Because you can see that even if we do not have a bearing capacity failure, we do have quite large displacements. And for many structures, a horizontal cyclic displacement of 40 centimeter would not be acceptable. So we should not focus only on capacity, but need to also think about displacements. And also for wind power structures, stiffness can be very important and be governing for the design. And then, of course, that's displacement may not then be acceptable. My last case is the model testing that we did on land for the Snorre TLP platform, which was in extremely soft clay. And the model dimensions are approximately 1 to 10. This shows one of the tests after it had been brought to failure. And the numbers to the right show the ratio between prediction, type A, and the measured failure load. The displacements were also quite good. You can see how the displacements developed with load. When we performed the test. This was done in the old days when we had the recording. We had a pen that went up and down when the test was running. And we had put our predictions in red before we started the test. And you can see how the pen followed our predictions. We were very happy during that test. You can also see the cyclic components compared to the predicted ones, which we are very happy with. So to round off, what I have tried to present in this oral presentation is that cyclic soil behavior depends on the stress path and the average and cyclic shear stresses, and that this can be put into contour diagrams, which is a very convenient form to represent this behavior. And these contour diagrams, that they provide parameters for capacity, displacements, and stiffness. And that we have verified this framework and the procedures that we use with this framework that have been verified by prototype measurements and model tests. We also think that the framework is a good basis to formulate and verify constitutive models, and also that it's a good framework when you are going to set up a laboratory program with cyclic loading. We have also a contour diagram or contour diagrams for various soils and densities. We also have correlations with index parameters, static and cyclic shear strengths, stress-strain relations, and also non-cyclic soil parameters like the initial shear modulus, friction angles, and consolidation characteristics, which may also be useful for other purposes than cyclic loading. The work that I presented is based on more than 4 decades of research and project work at NGI, and it has been done in cooperation with a large number of NGI colleagues, and it has been a very pleasant cooperation. It has also been a cooperation with colleagues in the industry, which has been very inspiring and rewarding. And it has not least helped us to identify needs and challenges that we have and guided the research that we have done. And also the support of the industry has, together with the Research Council of Norway, been in terms of funding, which of course is also essential for us. So that cooperation is very much appreciated. So finally, I would like to thank you for your attention at the end of a very long day. Thank you.
So it's my great pleasure on behalf of Technical Committee tonight to present you with the third Mcclelland Award. Thank you, Knut. Well done.
Thank you.